Hi, everybody. Welcome back. This is Mr. McCarson, and we're here with Unit 2, Part 3. This is on matter, and our topic for this video presentation on matter is physical change versus chemical change, which is also known more commonly as a chemical reaction. Okay, so when studying chemistry, we're concerned with the changes that matter undergoes, right? That's kind of our broad definition of what chemistry is. Now, there's two major ways that a substance that is comprised of matter can undergo a change. The first one we'll talk about is a physical change, while the second one is a chemical reaction or a chemical change. Now, a physical change is defined as a change in which the substance does not alter its chemical identity. So, for example, I can take a piece of paper and I can alter its physical property by crumpling it, but it's still paper. I didn't do anything to the chemical bonds that constitute the compounds that make the paper paper. Okay. Examples, and these are some good ones to write down in your notes. So, examples of physical change are things like freezing, melting, boiling, which, if you notice, are all changing the state of matter, where or what we call a phase change. So, if you have a piece of ice, which is solid H2O in your hand, and it absorbs energy from your hand and it melts into liquid water, the formula of ice or liquid water is still H2O. So whenever you change the state of matter, that's always a physical change. Cutting, ripping, condensation, tearing, crushing, those are all terms and descriptions that would allow you to identify something as a physical change. And the big thing there is physical change does not change the chemical composition or identity of the matter. Now, contrast that with a chemical reaction, a change in which one or more substances are converted into different substances. And so, one of the biggest examples is like, okay, so I've got paper, right? And this paper has a compound formula, okay? But as soon as I light it on fire, right, what's happening? We can see the smoke, we can feel the flame, you can see the ash. And now I've got fire and ash on my desk. Okay. Um, so burning is an example of a chemical reaction. Why? Because this paper, the portion that underwent combustion, is no longer paper. You can actually see one of the products. You can see that smoke coming off, that carbon dioxide, right? You can see the ash. So the edges are ashy. It's kind of all over my desk now everywhere. But that's a chemical change or a chemical reaction. Remember, we call the process of something that matter that burns combustion. Okay, so examples of chemical reactions or chemical change are burning, rusting, batteries charging up or running a battery, cooking, photosynthesis, cellular respiration. So there's tons of examples of chemical change, and part of the fun thing in this class is we're going to observe and study those chemical changes in reactions. All right, so I really like this slide. This is a good visual example of a variety of different things that could happen to matter that would be classified as physical changes. So you have things like crushing a soda can, so taking the aluminum and compressing it. It's still aluminum, it's not changing its formula. Melting an ice cube. Remember, whenever you observe a phase change, matter that is melting, freezing, evaporating, condensing, um, ionizing, right? Sublimating, going through sublimation, which we'll talk about. So any of our phase changes are always considered physical changes, not chemical reactions, because you're not changing the formula of the element or the matter involved. Okay, mixing sand with water, breaking glass, sublimation of dry ice, which is going directly from a solid to a gas state of matter, while skipping the liquid phase completely. Mixing green and red marbles, chopping wood, shredding paper, dissolving sugar in water. Okay, and once again, dissolving is a little bit more complicated. We're going to talk about dissolving in greater depth later this year. So, dissolving is kind of a weird one. It actually kind of straddles physical and chemical. The chemical properties of the water and the chemical properties and composition of the solute, whatever is being dissolved, allow it. But it's kind of a temporary process. So it is okay to classify dissolving as physical, but it's because of the chemistry and the chemical nature of the molecules involved between the solvent and the solute that it does occur. So that one's kind of like a tricky one, but we'll talk about dissolving in a lot more depth later this year. Okay, so moving forward into chemical change, which we can also call chemical reactions. Chemical change, chemical reactions are interchangeable terms. Any action that causes one or more substances to alter their chemical formulas. That's the big thing there. Like when I crumpled the paper, the formula of paper didn't get altered. The chemical bonds did not rearrange or change. When I lit the paper on fire, okay, we did actually have a change in the composition of the atoms and how they're bonded and arranged. Okay, we call that combustion. Now, chemical reactions are described by chemical equations. Now, you've seen these. The big thing about a chemical equation is you always know them because there's going to be a yields arrow or a reaction arrow in between. And then on the left side, we have the reactants. So the left side are the reactants. Those are the pieces of matter, the substances that will react with one another and alter each other in terms of their chemical bonding. And we say the reactants yield, and then on the right side, what we make, and this makes a little bit more sense with our current probably vocabulary skill, is the reactants yield the products. And we should all know, living in modern America, about products. Products are what you make. So here's an example. We have the formula H2 plus O2, and those are the reactants. They're on the left side of the reaction arrow, yield the product water. Now, that's not balanced, and we'll talk about balancing later in conservation of mass, but that is a skeleton equation for a very famous synthesis of water from hydrogen and oxygen. Okay, so here's some examples of chemical changes. Burning wood, right? That's very visible. There's a lot of evidence of chemical change there. Rotting fruit, baking a cake, rusting metal, using a battery, charging or depleting a battery, digestion, souring milk, exploding fireworks, cooking an egg, my favorite breakfast item. Problem is a little too much cholesterol for Mr. M right now. And then photosynthesis, which is a very, very big deal for life on planet Earth. So I hope this helps you understand what a chemical reaction is. And once again, we want to be able to compare and contrast chemical change versus physical change and be able to identify those in our labs and on exams and quizzes. All right, so what we're really going to be focused on when we get to lab here in the next week or so is evidence of chemical reactions. So one of the big things that we want to have young chemistry students understand is how do you know that something is undergoing a chemical change? Like when this paper is on fire, it's combusting. What is some evidence that you see, now that's all over the place, what is some evidence that you see that this underwent a chemical reaction or a chemical change, which it is still doing? Let me put that out on my desk. Okay, so first off, one of the major things is energy is absorbed or released. So it's either going to feel hot or cold. Something that releases energy to the surrounding universe, therefore it feels hot, is exothermic. Okay, so exothermic things feel hot. Like when we do combustion, when something gets lit on fire and it's burning, that's very exothermic. It's can be dangerously exothermic. Like when I lit that on fire, I felt the heat on my nose. I just need to make sure I don't singe my graying beard. Okay. Um, Endothermic is a chemical reaction which will absorb thermal energy from the surrounding universe into the system. And therefore, if you're touching something that's endothermic, it will feel cold. And you're going to actually get to experience that in a lab activity coming up shortly. Okay. So those are two big ones. Feels hot, feels cold. Those are good clues that you're undergoing a chemical reaction. Now, remember, these are not perfect. You still have to do a deeper dive. So, for example, if you're boiling water, it's going to feel hot. Don't touch the glass. Use the back of your hand. That's the right technique. Bring it up close to the glass, the back of your hand, maybe about an inch away. And if you can feel the heat, it's too hot to touch. Okay. in any case, getting away from lab safety, which is still always important. Um, if we boil water, it's going to have a great deal of thermal energy and it will give that off to the surrounding environment. But boiling water, evaporating water, is a physical change. So you do have to be careful. Okay, you do have to still look for matter changing its chemical composition at the core. One of the cool things you're going to see in the lab coming up, color change. So the paper started out white, and you can see around the edges it turned a kind of a darkish blackish brown. That's the ash that was created. The ash that I have sitting on my desk in front of me is a different color than the paper was. So a color change is a good indicator of chemical reaction. An odor change. When I lit that paper on fire, when you smell match burning, you know that there is a good chance that there's a chemical reaction, because an odor, when an odor is produced, something's altering in the chemical bonds. Rotting food, when things smell in your fridge and you go, oh, that's stinky, that lets you know that a chemical reaction has occurred and some kind of critters are digesting and breaking down that food, right? Whether it's bacteria or fungus, like molds, growing on bread, that smell lets you know that chemistry is occurring and it's a chemical change, chemical reaction. A precipitate. Now, a precipitate is a solid that separates from a solution. So if you take two liquids and mix them together, and all of a sudden, like a chunky or crystally solid will grow out of the liquid. And we'll do an example with this later this year with like rock candy. If you've ever had rock candy, that is a sugar precipitating out of a liquid solution. Okay, it's actually pretty fun to make. But that's what a precipitate is, a solid substance that comes out of reacting two liquid items together, is generally what we think of as precipitate. There's a couple of other ways precipitates work, but that will be for second semester. Light. Okay, when we burn the paper, you could see the light. Photons were emitted from the breaking and reforming of a breaking of old bonds and forming of new ones. Okay, so light being generated is a good uh, piece of evidence that you're observing a chemical reaction. And then what you're going to see a lot in this class, bubbling. Now, if there's bubbling, like let's say you mix a liquid with a powder and it starts to bubble, it's usually an indicator that a gas is being produced and released. Okay, now remember that these are only clues and not certainty. You actually have to dive deep into the reactants and look at the formulas and study what's happening with a deeper set of tools. But if you see any of these six, you're actually really on a good track that what you're observing is a chemical reaction. All right, so it's time to switch gears and look at states of matter. Okay, and we also know states of matter as phases of matter. So if you're state of matter or phase, it's largely the same thing. Those are interchangeable. So we're pretty familiar, by our age, we should be familiar with solids, liquids, and gases. And there's a nice diagram here that shows atoms arranged into solids, liquids, and gases. And the biggest thing are these kind of descriptions here for shape and volume. So solids have definite shape and definite volume. Like if you have a solid object like my Dodgers coaster, okay, this coaster has a volume, a length times a width times a height, and it has a definite shape. It's a rectangular cubic shape, or actually no, this would be square. Well, actually square and rectangle both, because all squares are rectangles. Okay, but this has a cube shape. Even though it's a little bit flat, it's still technically a cube. Now I can't squish this. I can't. It's solid, so like I can't. I might be able to compress it on a very very tiny level, but that's got definite volume and shape. Compare that with a liquid, which has a definite volume but an indefinite shape. We like to say that liquids are set volumes. Like in this is a 500 milliliter bottle of Kirkland water. Okay, Kirkland brand. I highly recommend it for your greatest liquid refreshment. Choose Kirkland. But the idea here is if I twist this bottle sideways, it's still got the same volume of water, but the shape of that water is now molded to the container based on gravity, right? So no matter how I rotate the bottle of water, it doesn't change its volume, but its shape changes based on the container and the forces of the universe. And on Earth, one of those greatest forces that affect shape is gravity, right? Pulling us all down, and sometimes pulls Mr. M down on that scale a little bit more than his wife's happy with. Now, gases are indefinite volume and shape. And the big thing about gases really is speed. What's the main difference between states of matter is energy. So like when you're a solid, this is really low energy. And now keep this in mind, all atoms move. The only time an atom stops having motion is at absolute zero, the coldest temperature in the universe. But like right now, to my eyeball, this LA Dodgers coaster, go Dodgers, doesn't look like it's moving. But on a deep level, the atoms are vibrating next to each other. In a liquid, the atoms are more fluid. Why? Because internally the liquid has more energy, right? So the temperature or the energy of the kinetic energy of the molecules, how fast they're moving, is greater here than it is here, okay, than it is in the solid. Now, for gases, they have the greatest average kinetic energy, which means gases like the air that I'm exhaling as I do this wonderful video, they're flying everywhere. They're bouncing into things, and we can do things like blow up a balloon. And what happens is the pressure of the gas molecules hitting the side walls of the balloon affect its shape and its volume. But if you let air out, the volume can change. And you can take a balloon and twist it and tie it and get it into all shapes, like when I go to Denny's and I try to get me a pirate sword from the balloon person there. Um, so remember that gases, indefinite volume and shape, liquids, definite volume but indefinite shape, and solids, definite shape and volume. Okay. Now, a state or a phase change is when a substance goes from one state to another. Now, very important, all phase changes are physical changes. Why? You're simply removing energy out of the substance to alter its phase. Like when we freeze something, we take like liquid water, and if we pull thermal energy out of the water molecules will solidify and form ice crystals. Okay. Now, how do we melt? We put energy back into the water, right? When we put a piece of ice on our hand, it melts because our hand is releasing energy. It's transferring from our hand into the water molecules, and that causes them to move around more. And eventually, they gain enough kinetic energy by raising their temperature where they become fluid in a liquid. Okay. Now, remember, temperature in chemistry is a really big deal. Temperature is not hot or cold. It's not hot or cold. It's the measure of the average kinetic energy of atoms or molecules in a system. And kinetic energy is the energy of motion. So, like gases move around really fast. Liquids are flowing. They're fluids, right? Liquids say they have fluid motion, okay? But they are not moving as fast as gases, which is why they're still confined. Gravity has more effect on them. And then for solids, what I want you to kind of imagine is the atoms are moving, but they're more like vibrating against each other in their shape, in their structure. Okay? So think of temperature as how fast or slow the atoms or molecules are moving. The higher the temperature, the faster the molecules are zooming around their container or the space they exist in. All right, now those aren't the only three states of matter. There's actually six total, okay? And the fourth one we're going to talk about a lot this year, that is plasma. Now, plasma is important because that's like the state of matter for the majority of our sun and our stars in our universe. It also what gives me great resolution in older TVs, okay? But plasma is defined as having a really high temperature but a low pressure, okay? And what happens is the electrons separate from the nucleus in plasma. So normally we kind of, and we'll get into it's not exactly this way, but we kind of imagine like electrons going around the nucleus. They move around the nucleus. In a plasma, they actually separate, right? Because the temperature is so high and the pressure gets to be so low. And we what we kind of misrepresent is like on Earth, we have solids, liquids, and gases, but in our universe, it's the most common state of matter. Why? Because it's the dominant phase of matter in our stars, like our sun. Okay. Now, the other two states of matter occur at very low temperatures. what we call absolute zero, which is the coldest anything can get. It's so cold that the electrons will stop moving around the nucleus of the atom, and funny things happen. So there's two actual, like we call them quantum superfluids. The first one was from Bose and Einstein. They mathematically predicted it, but it's called the Bose-Einstein condensate. And then another quantum superfluid that's more recent is the Fermi ionic condensate. Okay, from Fermi was another very famous um, chemist and physicist. He was very big when because he actually was part of the Manhattan Project. Was Enrico Fermi. So this was named after him, the Fermi ionic condensate. And what happens is they produce matter that it's kind of like a liquid. We call it a quantum superfluid, but it does really funny things. Now, this is a little bit above my pay grade in terms of being able to fully explain this because I'm not a quantum physicist. We'll watch some videos from quantum physicists that try to put this in terms that at our level right now we can understand. But the crazy thing for me is like this is where our future computers will operate. So like we have to get our for our quantum computers, our qubit computers that don't work on regular bits but quantum bits, they're going to do incredible things. But the one of the prerequisites is we get them close to absolute zero, if not to absolute zero. They have to be really cold to be able to do um, the wild loopholes in quantum physics that we're going to have these next generation of algorithms operate at. It's wild. It's wild, and I can't wait to share some of that with you. But smarter minds than me will have to help you on that journey. But we'll explore them together in this class later on. All right, so here's a very important diagram to add into your notes. And this is a phase change diagram. And what it's showing is how we move between different states of matter like solids, liquids, gases, and plasma, and what the term is for the phase change going from in one direction to the other. So, for example, if we go from a liquid to a solid, we know that as freezing. If we go from a solid into a liquid, we know that as melting. So you want to make sure you know these terms. A gas going to a solid is known as deposition. A solid into a gas is sublimation. A liquid into a gas is vaporization. A gas into a liquid is condensation. A gas into a plasma is ionization. And a plasma back to a gas is recombination. So make sure you're familiar with those terms. And a quick note, liquids to gases is evaporation, or sorry, vaporization. Evaporation is specific to water, liquid water turning into steam or water vapor or water in a gaseous state. Okay, now the other thing I want you to pay attention to over here is this enthalpy of a system. This is a fancy way of saying the energy in the matter. So, for example, the highest energy state of matter is going to be plasma. To go from a gas to a plasma, you have to add a ton of energy. And if you think about stars, why are stars plasma? Because of the nuclear fusion going on provides so much energy. The normal state of matter there is plasma. Okay. On the low end, our lowest energy phases, our phase is a solid. So to make a solid, you're removing energy out of the matter, out of the system. So make sure you know this diagram. This is an important one. And remember, all all phase changes are physical changes, and you're either adding or removing energy from the matter to get it to phase change. Now, when we talk about properties of matter, we have a couple of ways that we can classify. We have physical properties versus chemical properties. Now, a physical property is a characteristic that can be determined, and here's the key phrase here, without changing the chemical identity of a substance, okay? Without altering its chemical composition or its bonding. So, like measuring the length of a sample is a physical property, length, but it doesn't change the identity of the atoms or molecules or compounds. Okay. Color is a physical property. Density, you can measure density of gold without turning gold into something else. Mass, elasticity, how stretchy it is. Pressure, volume, or luster. Luster is how shiny a material is. Okay, so these are all good examples to take down of physical properties of matter, which are properties that can be determined without changing the chemical identity of the substance. All right, next we have chemical properties. Now, chemical property is a characteristic that relates to a substance's ability to undergo chemical changes that transform it into a different substance altogether. So, if it's got a chemical property, that means we have to chemically react it to see if it has that property. So, the probably greatest example of this is flammability. If you want to know if paper's flammable, you have to do what? You have to light it on fire. Okay? And if you light paper on fire to see if it's flammable, you can answer that. But does the paper still exist as paper? No. It's undergone a chemical change. So examples of chemical properties are toxicity, oxidation states, we'll talk about that later, heat of combustion, chemical stability, flammability, enthalpy of formation, possible chemical bonding, reactivity, and coordination number. Now, a lot of these are a little bit more complex, and we'll get into those. Really, the big one to kind of always think about is flammability is really a good example of a chemical property. How do you know if something's flammable? You burn it. And if you burn it, you can't unburn it. Okay? So those are chemical properties. Now, the final way that we classify properties of matter is we look at them as either extensive properties versus intensive properties. Now, extensive are measurements or properties that depend on the amount of matter that is present. So, for example, if I eat more food, what will happen to my mass, the actual mass of my body? It will go up. Okay. If I take a balloon and I um, push more air in with more air pressure, the volume of the balloon will increase. So, an extensive property is a property where the measurement of the property, the value or the number related to the property, changes as the amount of matter increases or decreases. Now, an intensive property does not depend on the amount of matter present. So, things like melting point, density, ability to conduct electricity and heat. And really, the big one is density. Like if you have a tiny gold ring or a huge gold chain, if it's pure gold, no matter how much sample you have, the density will be the same. Okay, so those are examples of intensive and extensive properties. And extensive are things like volume, mass, the amount of energy in a substance, those change with the amount. Density, melting point, boiling point, freezing point, those don't change. Like if you have ice, whether you have a huge iceberg or a little ice cube in your drink, ice's melting and freezing point is 0 degrees Celsius, okay, under pure water and atmospheric pressure. Okay, so these are very important to know the difference between extensive and intensive. All right, final slide for this part 3 of matter and properties of matter. These are just some examples of intensive properties: boiling point, color, temperature, luster, and hardness. The amount doesn't matter, it doesn't change how these are measured. Extensive properties, where the amount of matter or the amount of matter changes the property: volume, mass, size, weight, and length. So these are good examples to make sure you have in your notes to get ready for the quiz next week. All right, everybody, have a great day. Thank you for staying with me through this lecture series on properties of matter. Don't forget to smash the like button. We'll see you in class. Bye.